All right, so now what we're going to do is discuss this notion of the region of absolute stability. So recall you had the characteristic polynomial, which depends on h and lambda, right? So you have phi of z is p of z minus h lambda q of z, right? And so initially, it's like when we studied this idea of astability, what we did was to ask whether or not all the roots, so in astability, right, one asked if all the roots of phi of z lie in this unit, this sort of open unit disk, right, when h is greater than 0 and the real part of lambda is less than 0. Okay, so so the basic question then is, again is under what conditions? So let me rephrase that. We can turn this around. It's like and ask under what conditions. It's like do all the roots of phi of z lie in this disk where the conditions are on h and lambda instead. All right. So in the region of absolute stability, well, okay, so let me just say it this way. So the region of absolute stability sort of refers to the values of h times lambda where all the roots of phi z lie in this disk modulus of z is less than 1. Okay, so if we think about it for a second, right? So the condition that the real part of lambda is less than 0 and h is greater than 0 together, when you multiply h and lambda together, that's equivalent to this is equivalent to the condition that h lambda is in the left half plane of the complex plane. Okay, right. So yeah, so h if h is scalar valued and it's positive, then h times lambda, the condition that the real part of lambda is less than 0 and h is greater than 0 is equivalent to saying that the real part of h times lambda is less than 0, right? So those are equivalent. Well, let me rephrase that, right? Not equivalent, but so the real part, yeah, so this implies this, right? Okay. Okay. Anyway, so yeah, so again, it's like this notion of the region of absolute stability refers to the points of in the complex plane. It's like where h lambda is allowed to lie in, where this characteristic polynomial it's like has roots which are all in this unit disk. Okay. So the remark is that a method is astable, right, if the region, its region of absolute stability contains the left half plane. Okay. So yeah. So again, it's like this allows you to have a little bit more power because yeah, it's it's like it gives you a way, if you will, to weaken this condition of astability by instead looking at this notion of the region of absolute stability. So it may or may not contain the left half plane. It's like, but nevertheless, it's like the value is h times lambda, where the method is still going to perform reasonably well. Okay. All right. So let's look back at the Euler method, because the Euler method was what initially motivated our study. It's like of this idea of astability in the first place. So it's not astable, but we can still ask, it's like, what is its region of absolute stability? So let's an example. What is the region of absolute stability? For Euler. Okay, so I'm going to write Euler in this sort of general linear form. Xn minus xn minus 1 is equal to hf n minus 1. So this P of z is going to be z minus 1. Q of z is going to be just 1, right? So phi of z is going to be z minus 1 minus h lambda. Okay, and I'm going to call this W, all right? Okay. So the root, there's only one root. The root of this characteristic polynomial, right, is z equals to 1 plus W. Okay. So for the root to lie inside the unit disk in the interior of the unit disk, right, we need that the modulus of 1 plus W is less than 1. So you can sort of draw a picture here, right? So this is basically saying that, so I can write this as W minus 1, right? So this is saying that the distance from W, it's like to the point minus 1, right, is less than 1, right? So we can draw that as a minus 1. So this is the region of absolute stability for the Euler method. Okay, so the region of absolute stability for Euler, right, is the open disk, open unit disk centered about minus 1. Okay. All right, so clearly it's like this is not astable, right? Because in order for it to be astable, the region of absolute stability must contain the entire left half plane, not including the imaginary axis. Okay, yeah. So so the basic idea, if you will, is that what you want in practice for the method to be reasonable is that you would ideally like it that this region of absolute stability, even if it's not containing the entire left half plane, it would be still sort of nice if it contained things like an array of this form, right? Because if it contained, it's like this kind of, it's like these rays, right? So if you contain sort of this kind of segment, then for certain values of lambda, right, it doesn't matter what time step you take, it's like it would still be contained in the region of absolute stability. So, the problem, if you will, is that this condition for astability, which is to say that the region of absolute stability contains the entire left half plane, is extremely restrictive, as was sort of observed. It's like by Dahlquist, right? So Dahlquist showed that if you look at linear multi-step methods and you want them to be astable, then they have to be implicit and they can have at most order 2, right? So that's an extremely restrictive condition. So what you can hope for is to maybe relax that condition by, instead of having the region of absolute stability contain the entire left half plane, if it sort of contains these kind of, it's like segments like this, it's like it's still not so bad, right? Because it's like if you look at the problem, it's like, and your lambda, it's like are say all clustered here, then you can take arbitrarily large time steps and with the method which is not astable, but it has again a stability region which contains these kind of arcs here. Okay, so that's sort of the basic idea behind this. This is the reason why we also are interested in these regions of absolute stability, because they give you a more nuanced notion of for what values of h times lambda, it's like the method is still going to behave the way you expect it to behave. Okay. All right. So in fact, it's like there are some methods which are very dissipative. All right, and maybe it's like at this point it's worth looking at this region of absolute stability for the backward Euler method, right? So let's go ahead and see what happens. Okay. All right. So for backward Euler, right, we have that xn is equal to xn minus 1 plus hfn, right? So this is xn minus 1 is equal to hfn. So this tells you that p of z is equal to z minus 1, q of z is equal to z. So phi of z is z minus 1, right, minus h lambda z. Okay, so I'm going to call this w, right? So this is 1 minus w z minus 1 is equal to 0. So z is equal to 1 over 1 minus w. Okay, and so we want this to be at absolute value less than 1. Okay, so I want the absolute value of z to be less than 1. So this is 1 over absolute value 1 minus w to be less than 1. I can multiply it on both sides, right, by the sort of the modulus of 1 minus w. So this gives me 1 minus w is bigger than 1. So again, it's like if you think about this, this is the distance between w and 1. All right, so now this you have a disk centered about 1 now. All right, and you want the set of points where it's outside this. Okay. All right, so it's not actually containing that as well. So what you can see basically is that the region of absolute stability for the backward Euler method is actually all the points except for this closed ball of radius 1 centered about 1. Okay, so let's think about that for a second. So amongst other things, this tells you, this sort of analysis of the region of absolute stability tells you that the backward Euler method is astable because the region of absolute stability contains the left half plane, right, which is sort of the condition for astability in terms of the region of absolute stability. But there's also an interesting point, right, because if you remember, when lambda is negative in real value, it has a solution which decays. Okay, so what this is actually telling you, this region of absolute stability calculation is telling you, is that when you apply the backward Euler method to values of lambda, it's like with real some of the real, it's like, well, it's like you apply it to a differential equation where the lambda, it's like has a real part greater than 0 in some instances, right? So outside this ball, right, you could still have a situation, or you actually still have a situation where the Euler method is dissipative, right? So now you have a situation where, it's like for certain regions here, for certain values of lambda, you actually have a numerical method whose exact solution is exponentially increasing now. But when you apply the backward Euler method to it, it is still going to decay. Okay, so that's something to be aware of, right? I mean, it's like, so the same way that the forward Euler method has a situation where, it's like when you apply it to a problem where the solution is decaying, you could have a situation where the numerical method is blowing up, right? Here, with the backward Euler method, you have sort of the opposite problem, where if you apply the backward Euler method to some problems where the solution is exponentially increasing, you still have a numerical solution which is decaying. Okay, so that's something just to be aware of. Okay, so so let me sort of just finally wrap up by saying, well, what happens if you have a nonlinear system, right? Because so far we've been talking about how the method behaves when you apply it to a model problem, which is expressed in terms of a linear system of equations. So let's see what happens when it's nonlinear. And the basic idea, if you will, is that if it's nonlinear, you replace it with its linearization, and you look at the properties of that linear system. And that's still going to tell you something about these stability properties. Okay, but let me sort of just be a bit more precise with this. Okay, so now with nonlinear systems, okay, so you have x prime is equal to f of x, for example, right? Then you can linearize it, so we can consider its linearization. Okay, so you can write this as x prime is equal to f of x0, right? So essentially we're looking at the Taylor expansion of this, right? Plus j x0 x minus x0, right? So this is the Taylor expansion, if you will, to order 1, right? Where j is just a Jacobian, right? This, and jij is the partial of fi with respect to xj. Okay, all right. So yeah, so you replace, it's like a nonlinear differential equation, but it's a linearization about the point x0, where again this j is the Jacobian matrix, right? So this Jacobian. Okay, so so basically it's like now it's like when you want to see whether or not this system is stiff near the point x0, you look at the properties of this Jacobian matrix, right? So to determine stiffness, right, we look at the eigenvalues of the Jacobian matrix. J at x0. Okay, so if the system is stiff, right, then what is going to happen is that the eigenvalues are going to have the property that the real part of lambda 1 is less than or equal to the real part of lambda 2. So there's some sort of inequality, sequence of inequalities. This is less than 0. And the difference between this is very large. And real part of lambda 1 is a lot less than the real part of lambda n. Okay. So in order for the multi-step method, it's like to perform well, it's like for such a problem, if it happens to be stiff, then you need to look at all these real parts. It's like, and basically make sure that it's like the h times lambda i's are in the region of absolute stability. So so for a multi-step method to perform well on such a stiff problem, you want the region of absolute stability to contain sort of h lambda 1 all the way up to h lambda n. Okay, so that's the basic idea behind this. Okay, and then so you can, oftentimes you can then pick h, it's like so that that condition holds. All right, so that's basically what we wanted to say. It's like for solutions of differential equations as well as systems of differential equations. So the next thing we'll be talking about are sort of the generalization of these things to partial differential equations. So let me stop here for now.